Well, fellow astronomers, at home, abroad, in Peyton Hall, wherever, welcome to the December meeting of the Amateur Astronomers Association of Princeton. As you may or may not know, my name is Larry Kane. I'm the Associate Director, Assistant Director, whatever. And our director is somewhere in the Middle East, I believe. So, I was planning on kind of just keeping everything brief, mainly this evening, and concentrating on a few business issues after our speaker. This is the agenda as I foresee it. Anyone is certainly welcome to add anything to it. What I'd like to do just before we break for traditional relaxation and stretching is just to open it up to anybody in the meeting to find out what they think of this meeting and the club in general, and if they have some suggestions they could offer. So we can get to that. What I'll do right now is call on our program manager, Victor, who is going to introduce our speaker for the evening.
Okay, well, let's press on. It's my pleasure to introduce our guest speaker tonight. His presentation is titled Exoplanets, Science and Science Fiction. For centuries, people have wondered whether the stars in the sky harbor planets of their own. Astronomers began discovering such exoplanets in the 1990s, and by this point, more than 6,000 are known. One reason to study exoplanets is to learn about the process of planet formation. Another is to seek planets that might be suitable for life as we know it. This presentation will concentrate on a less scientific reason to try confirming science fiction. Does the universe really contain lava-covered planets, planets with two suns, planets near black holes, and other worlds familiar from science fiction? Our guest speaker tonight is Joshua Winn. Good, I'm really doing great tonight. Josh Winn's research goals are to explore the properties of planets around other stars, understand how planets form and evolve, and make progress on the age-old question of whether there are other planets capable of supporting life. His group uses optical and infrared telescopes to study exoplanetary systems, especially those in which the star and planet eclipse one another. He was a participating scientist in the NASA Kepler team and is a co-investigator and architect of the ongoing Transiting Exoplanet Survey Satellite, or TESS mission. Over the years, he and his group have also pursued topics in stellar astronomy, tidal evolution, planetary dynamics, radio interferometry, gravitational lensing, and photonic band gap materials.
Okay, so thanks everybody for coming out. Thank you for those of you who are tuning in online. It's nice to see everybody again. I think I was last here about 6 years ago. So either I didn't do such a terrible job then, or there's just been a lot of turnover in the leadership of the club and you don't remember it. In any case, it's nice to be back. So this is going to be a very serious academic type lecture because I know the level of intelligence in here is very high. So we will start by going to the most important text in this area of science. This one. All right, so I have the sound off. So right now you should be hearing the John Williams score, and this will serve as my introduction. Rise of exoplanets. An exoplanet, for those of you who don't already know, is a planet that orbits a star outside the solar system, besides the sun. For centuries, people have speculated about other worlds. Science fiction invites us to imagine exotic planets such as Tatooine, Arrakis, Trisolaris, could similar planets really exist? Only since the 1990s has it been possible to discover planets around other stars. Some of the known exoplanets resemble science fiction worlds. Others will inspire new stories. The problem with trying to find and study exoplanets, and the reason why it took until the 1990s to do it, is that in the first place, the stars are very far away. I don't need to tell you that. We were talking about scale models at dinner. One that I looked up is that if you shrank the sun to the size of a grapefruit, then the Earth would be about 40 feet away. So I guess that means it would maybe not quite fit into this auditorium, probably be the size of a poppy seed, 100 times smaller than the sun. And the nearest stars would be several thousand miles away. So certainly visiting exoplanets with spacecraft is completely out of the question at the moment. And everything we know and everything we will learn for the foreseeable future comes from telescopes with the best technology that we can put on those telescopes. One problem, even for telescopes, is that planets are much smaller and fainter than stars. So the problem has been compared to trying to see a firefly.
Sorry to interrupt.
Yes.
Occasionally your mic is either touching your neck and it's coming in garbled or over Zoom. So
Maybe I can just hold it.
to the side?
Yeah, or I can just hold it like this. I don't mind. How's this?
That or this?
Maybe let's do that. It's a little easier
that's better. It's just that it's sometimes when you move or something like that, you hear your voice getting garbled.
Good. Yeah, I appreciate you telling me so that everybody online can hear me better. So, in light of these problems, how do we find and study exoplanets? And let's start in the realm of science fiction with Alpha Centauri. The nearest stars to our solar system shows up in science fiction all the time because it is only 4 light years away. So that's where the Robinson family was in Lost in Space. That is where the planet with the moon Pandora is located in the blockbuster Avatar. Are there exoplanets around Alpha Centauri? Well, some of you may have enjoyed going to the southern hemisphere and actually seeing Alpha Centauri. So this is the constellation of Centaurus. Here's the famous Southern Cross. And this is Alpha Centauri. So to try to find exoplanets, the first thing you might think of is gain access to one of the world's best telescopes, say the Hubble Space Telescope, point it at Alpha Centauri, and you'll see the star, and you look for little dots of light that are orbiting the star. Well, if you try that for Alpha Centauri, this is what you see with the Hubble Space Telescope. There's 2 stars. That's the first thing you learn. Alpha Centauri is actually a binary star. These 2 stars orbit each other once every 80 years or so. Now, are there planets around either of these stars? Well, it's going to be awfully hard to tell because the stars are so bright that they saturate the detector. All of these pixels are lit up to their maximum value. And even worse, there's a halo of bright light surrounding each of these stars. If we could focus light arbitrarily tightly, then you would see, given the angular size of these stars, they should just each occupy 1 pixel in the image. But we cannot focus light as tightly as we might wish because of the basic laws of optics, specifically the laws of diffraction. That light waves, whenever you interrupt them with a telescope, for example, an opening of a telescope, they splay out. And so as a result, the light from a star, which is coming from one singular direction, appears to be coming from a range of directions, and that leads to this spillover effect on our image. If there were an Earth-like planet orbiting at an Earth-like distance around Alpha Centauri A, its orbit would be about this size. Hopefully you can see on your screen this tiny little dotted line. And that, if there is such a planet there, it would be 1/1000th of the brightness of the star and completely lost in the glare of the star. And these are the nearest stars. It's even harder for stars that are farther away. So that's the problem. And we do not know at this moment of any planets around either of the 2 stars in Alpha Centauri. Doesn't mean they're not there, just means that the searches to date have not turned up anything. On the other hand, you may also know that the two stars of Alpha Centauri are not actually the nearest star to the sun. There is a third star in that system, Proxima Centauri, which is faint and inconspicuous. You cannot see it with the naked eye. It's 11th magnitude, for those of you who know magnitudes. And it's probably orbiting around the pair of stars in Alpha Centauri, and it happens to be a little bit closer to the sun at this moment in its orbit than the two stars are. So Proxima Centauri is literally the closest star to the sun. And we do know of at least one planet, and probably two, that exist around Proxima Centauri. But they don't come from the method of direct imaging. They don't come from trying to see the planets as points of light in the image. What's even more exciting is that one of these planets, Proxima b, is located within the so-called habitable zone of the star. That we define as the range of distances from a star where the star's heat would raise the surface temperature of an Earth-like planet to allow for liquid water. So it would be between 0 and 100 degrees Celsius. And we call that habitable or potentially habitable because we think that that water, liquid water in particular, is a necessary element for all life forms on Earth. So if we want to look for life elsewhere, maybe we should prioritize those planets with liquid water on their surfaces. So the very nearest neighbor to the sun has one of those planets, which is very exciting. This discovery was announced probably about 5 years ago at this point. And if you remember that, if you saw the announcement in the newspaper or online, it was probably accompanied by this spectacular image of the view from the planet's surface. All right, this is Proxima Centauri. These are the two stars of Alpha Centauri way in the background, and there's this beautiful valley, and looks like there's even some mist rising from the valley. Of course, this is a complete fantasy. We have no idea what it looks like on the surface of this planet. Everything we know about this planet comes from a chart like this one, because this planet was discovered in a very different way. What we're seeing here is speed, and that's speed of the star towards or away from us as a function of time in days here. The underlying physics behind this technique is that when a star has a planet, we say that the planet orbits the star, but the more precise statement is that both the star and the planet orbit around their common center of mass. And the star is much more massive than the planet, so the center of mass is close to the center of the star, but it's not exactly at the center of the star, so the star moves around as well. And that's what gives us our way in, because we've gotten very good at measuring the motions of stars. And we do that using the Doppler effect. So for those of you who need a little reminder about what the Doppler effect is, and this is again where I would have had some audio from my computer, this is the Doppler effect. That's the Doppler effect. It happens whenever you have a source of waves that is moving relative to the observer. In the forward direction, the source is catching up to its own waves, and so the distance between the crests of the wave are compressed, and for audio, that means higher pitch. And in the backward direction, the source is moving away from its own waves, causing the wavelength to be longer, which means lower pitch. Same thing happens for any type of waves, including light. So a car with its headlights on coming towards us would have the light from its headlights shifted to the blue side of the spectrum. Shorter wavelength for light means slightly bluer. And likewise, if it's moving away from us, the light is redder. And we never notice this in everyday life because it is a tiny effect. The fractional change in wavelength is equal to the speed of the car, or whatever the source of light is, divided by the speed of light, which is obviously very big. And so that's why we never notice this is happening, but we can certainly build special purpose equipment to detect these tiny changes in wavelength. And that's what allows us to sense the motion of the star around the center of mass of a planetary system and deduce that there's a planet there even when we cannot see it in an image. So that's what we're looking at here, is the motion of the star towards and away from us as it orbits in a little circle around the center of mass. And the red points and the blue points are the data that were gathered over 2 different seasons. The amplitude of this back and forth motion tells us about the mass of the planet. The more massive the planet, the more it will pull around the star. And the period tells us the orbital period of the planet. So those are the 2 basic things we can learn. The surface features, the geology, all of that is for some generation, far in the future. For now, the type of information we can gain about exoplanets is quite limited. I'll show you how we can get a little bit more, but not nearly as much as we will ever have for planets in the solar system. This is another famous Doppler discovery, 51 Pegasi b. Here, the Doppler velocity, this is a sun-like star that is moving back and forth with a speed of around 70 meters per second, either way. That tells us this is a giant planet, roughly half the mass of Jupiter. But the period is only 4 days. If you look at the label here, this is time in days. So this was one of the first, maybe the first, really big surprise in exoplanetary science, the existence of giant planets, presumably like Jupiter, but that have much smaller orbits than Jupiter does. These are the so-called hot Jupiters. And it won its discoverers, Michel Mayor and Didier Queloz, half of the Nobel Prize in Physics in 2019. The other half was earned by our colleague here in the physics department, James Peebles, for his work on cosmology. All right, back to science fiction. In one of the Star Wars films, Anakin Skywalker and Obi-Wan Kenobi duke it out with their lightsabers on a planet that is completely covered with lava. Do such planets exist? And the answer appears to be a pretty firm yes. There is in a new emerging category of known planets called lava worlds. And I'd like to explain how we make that inference. It doesn't use only the Doppler method. In this case, it uses a method based on eclipses or transits. So what you're looking at now is a movie that was made in 2012 during one of the rare transits of Venus across the sun. Maybe some of you even saw that event. There was a lot of public activity relating to it. And the thing is that it was interesting and fun, but it's not a dramatic event. If you didn't know it was happening, you have to be told, right? It's not like the sun suddenly goes dark, like in a total solar eclipse. Nevertheless, they're very interesting, and the sun does get slightly fainter. The light we receive from the sun, part of it is blocked by Venus when this happens. And that again gives us a way to detect exoplanets, because surely the same kind of thing must be happening even for distant stars. If the orbits of the planets are lined up along our line of sight, then every time the planet goes in front of the star, we should see the star get slightly fainter because the planet is blocking a small fraction of the light that usually reaches us. So this is called the transit method. And what we learn is from the amplitude of these dips, we learn the size of the planet, the size of its shadow relative to the disk of the star. And again, we can get the orbital period from the time elapsed between these transits. The planet makes a transit every time it comes around. So with this method, we can collect data like the one I'm showing, like the data set I'm showing here. This is for a planet called Kepler-78. And what we're looking at in this case, the horizontal axis is time, and the vertical axis is the drop in brightness relative to its usual brightness, so that's 0, and it's expressed in parts per million. Now, the Earth moving in front of the sun, if you were viewing that from 10 light years away, you would see the sun get fainter by 100 parts per million. So in this case, there was something that moved in front of the star that blocked about 200 parts per million. And since the size of the signal depends on the cross-sectional area of the planet, that means that the diameter, so the cross-sectional area was twice that of the Earth, put it that way. So it's not that much bigger than the Earth, probably a rocky planet. And that's borne out by mass measurements of this same planet. But what's interesting is the horizontal axis. So now the time is being expressed in hours. This is a planet that makes a complete orbit every 8.5 hours, which is about as close as you can get to a star without being in danger of being ripped apart by the tidal gravity or just having the heat from the star start to do bad things to the surface of the planet. You can also see that in addition to these dips here, there is a second dip here. It might just look like a statistical fluke, but actually no, this is a significant dip here with a much smaller amplitude halfway between the transits. What's going on here is interesting. So we can't see this happening, but what's going on is the planet moves in front of the star, and that's when we see these big dips. And then it keeps going around, and its hot illuminated day side comes into view. Now we can see the bright part of the planet, and that's why there's a gradual rise in the total light that we see from the system. And then the planet is hidden by the star, and that light disappears. And that explains the second dip here. So by measuring the size of this dip, we can say that that is determined by how much light is coming from the planet, which in this case is a mixture of the reflected light from the star and its own heat emission, its own thermal emission. It's glowing because it's so hot. So by measuring this and modeling it, we can determine the surface temperature of this planet, and it's several thousand degrees, certainly above the melting point of most of the common rock-forming minerals that we know exist in the solar system. So that is the basis for our inference that this and other similar planets are lava worlds. The side of the planet facing the star, at least, is certainly hot enough to create a gigantic magma ocean that might be a third of the planet's surface. So we tell our friends who are space artists this information, and they tell us, oh, well, this is what the planet's surface looks like. So they, science and science fiction and science art all go together. These kinds of images not only excite the public, they also get us thinking too, to get beyond the dots on a chart and start to think in broader terms about what we might look for, what we might hope to see someday by studying exoplanets. Next, okay, here's another data set that shows brightness versus time. In this case, time is in days. So if you look at this top chart, you see that the star is basically constant in brightness, but then every now and then it dips down, but by a large amount. So in this case, the dip was down to 0.83 or so. So 17% of the light was blocked, and here 20% of the light was blocked. This is not a planet eclipsing the star. It's too big. This is a second star. This is two stars orbiting each other, eclipsing one another. But then in addition to that, if you zoom in on this part of the data set here, that's what's shown in the lower chart, where the y-axis has been zoomed in right around 1. You see that there's another smaller dip that is of a planetary type amplitude. So what's going on here is that we have two stars, like I said, orbiting one another. We are viewing this from the side. So we see the red star eclipse the yellow star. We see the yellow star eclipse the red star. But maybe you've also seen by now that there is a planet looping around both of them. And every time it comes in front, it eclipses one star and then the other. And we can see all of those events in the total brightness record that we have from this system. So this is a so-called circumbinary planet, a planet whose orbit surrounds a pair of stars. And what does that remind us of? Oops, sorry. This, of course, brings to mind a certain farm boy from Tatooine looking out at the desert sunset and seeing two stars. So these circumbinary planets, we only know of about, say, 15 or maybe 20 at this point, but they are hard to detect. And based on the level to which they've been searched and the number of stars that have been searched, we can conclude that they're not very rare. That as long as you are far enough away from this pair of stars, say 5 times the separation between the stars, if you move out that far at a safe distance, planets there are just as common as you find around single stars of similar type. So there are lots of these circumbinary planets in the galaxy. Here's a diagram showing 2 of them. This one is Kepler-16. It was the first one to be discovered. There are, again, 2 stars going around the center of mass of the whole system, and there's a single planet going around both stars. My favorite is Kepler-47 because there are 3 circumbinary planets, each of which transits both stars when it comes around. So it's a very edge-on oriented system. Another science fiction novel I found interesting was The 3-Body Problem by a Chinese author, Liu Cixin. I think I'm something like the way it's supposed to be pronounced. I don't know if any of you have read this. I recommend it. It's very weird. And it is about, it involves contact with a civilization that has 3 stars in their planetary system on a chaotic pattern of orbits. So the system is unstable over the lifetime of the civilization. And the book explores the ramifications that would have for the creatures on these planets. So are there planets that have 3 stars or that have chaotic arrangements of orbits within the planetary system? Well, the answer is certainly nothing as dramatic as in this book, but there are some systems that are right on the edge of instability and chaos. And my favorite example is Kepler-36. This is another one that was discovered with the transit method. We have the central star here, and we have 2 planetary orbits, 2 known planets, and the orbits are here drawn to scale, on the same scale as the star. So these orbits are very close in to their star, and they're very close to each other. They're practically sharing the same orbit. The ratio of their orbital periods is very nearly 7:6. To see the planets, we need to zoom in by another factor of 50. The inner one, roughly the size of the Earth, the outer one more like Neptune. And because their orbits are so close to each other, they're so closely spaced, every time one planet laps the other one, they pull on each other with their own gravitational forces. And that causes a perturbation in their orbits. And as a result, the transits that we observe are not exactly periodic. So what's plotted here is the deviation in hours of the observed transit from when you might expect it if the transits were very regular. Sometimes the planet arrives 3 hours late, sometimes 3 hours early relative to a periodic schedule. And it has this kind of jiggy-jaggy pattern. On even longer time scales, it rises and falls and becomes kind of hard to track. And over about 10 years, we don't have the ability to predict where these planets will be located because of the accumulation of these perturbations. That's the technical physics definition of chaos, sensitive dependence on initial conditions. We don't know the current state of the system well enough to be able to predict where it's going to be 10 years from now, because that outcome depends so sensitively on where the planets are now. And that would even be true for any creatures living on these planets. They probably wouldn't be able to predict out more than, say, a century or 2, even if they have really good knowledge of where their planets are now. They lose the phase of this signal, basically. So this is a system that really is on the brink of chaos. If these planets had been a little more massive than they really are, the system would have fallen apart. The planets would have collided. One of the planets might have fallen into the star. So it's a bit of a puzzle to understand how this system came to be in this seemingly fragile state. It also brings to mind a classic short story by Isaac Asimov called Nightfall. This is a story in which there is a planet, Calgash, that is in a planetary system with 1, 2, 3, 4, 5, 6 stars. And because of that, the surface of the planet is always illuminated by at least one of these stars, except for every few thousand years when all of the stars are either below the horizon or eclipsed. And that leads to darkness, nightfall, which freaks out everybody on the planet. They've never seen darkness, and the civilization collapses. And this happens periodically. So a very interesting story. Do we know of any planets that belong to a crazy multi-star system like this one? We do know of star systems like this. We know of a whole bunch of them. One of my favorites is this one. It doesn't have a cute name. It's test input catalog number, da, 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 da. But what we see here is the brightness, the total brightness of this system, which is all that we can measure, seems to vary erratically with no particular pattern. And that is because in this system, there are 6 stars. And we're viewing the system edge on. So there's 2 pairs of stars orbiting each other, and then there's another pair of stars orbiting around all of these 4 stars. So this is a real system. We can see all of the various eclipses. This is a sextuply eclipsing star system, but we don't know of any planets, unfortunately, around these stars. It's plausible that they exist, but we don't have the data to do a very sensitive search for planets around these stars. But at least we know these star systems do exist in this case. This, by the way, was a discovery that was made by an ongoing NASA mission that is the main engine of our discovery these days in exoplanets. It's called the Transiting Exoplanet Survey Satellite. It uses these 4 lenses, these 4 small telescopes, each of which has an opening of 10 centimeters in diameter, to scan large chunks of the sky looking for these brightness dips from orbiting planets. And it has discovered thousands, maybe at this point about 6,000 exoplanet candidates. That is, signals that resemble the dips from transiting planets. Most of those still need to be confirmed with further analysis. Nevertheless, a whole bunch of new planets and other variable objects are being discovered by this amazing mission. Okay, what about the famous stars in the sky, like the stars of the familiar summer triangle, Vega, Deneb, and Altair? And I know we had a question on the board here. What about Altair 4, which is from a science fiction movie? The great thing about TESS is it is collecting data from the entire sky, including all of the brightest familiar stars. However, it has not detected, and nobody has detected, any planets around stars similar to these. And that's because these are massive stars. They are more massive than the sun. And that creates all kinds of problems for our planet detection methods. Transit method doesn't work because these stars are big, and that reduces the amplitude of any transit signal of planets going around them. The transit method also statistically is unlikely to see planets around a given star because the orbits have to be aligned just so. So the transit method doesn't work. The Doppler method doesn't work for a more complicated reason, which is that these massive stars tend to rotate very quickly, much faster than the sun. And that broadens out the features in their spectra and prevents us from doing really precise Doppler measurements. So that is why many of the famous stars in the sky, we would love to know if planets exist around them, but we cannot detect them. We cannot perform a significant search with the transit or Doppler methods. However, massive stars are perfectly good for the direct imaging method, which I said at the beginning was essentially impossible, but it is not totally impossible. And some of the greatest successes we've had with that imaging method of seeing dots in an image have come from looking at massive stars. So in particular, this is the Great Square of Pegasus here. And there is a star at 6th magnitude right along one of the arms here called HR 8799. It is a massive star, kind of like Vega and Altair and Deneb. And when you make an image of this star with one of our best telescopes here on the ground, an 8-meter telescope, this is what you see. There's no planet visible in this image. This is just the star spilling light all over the detector because of diffraction, the problem that I mentioned at the beginning. But some of my colleagues are very clever and build devices called coronagraphs. And I won't labor to try and explain how they work, other than to say that what you do is you place 2 carefully contrived obstacles in the optical path of your telescope that have the effect together of blocking the light from the central star while allowing any other sources of light in the image, even if they're very faint, to come through and to be registered on the detector. So using a coronagraph and observing that star, HR 8799, this is the resulting image. So the black circle in the middle is where the star has been blacked out, and there's lots of artifacts here that are just covered by this black circle. You can see that it didn't work perfectly. There's still some light spilling out from around the rim here. But you also see this dot, this one, and this one. Those are planets. Those are definitely planets. They're not artifacts. And one of the reasons we know that is this system has been observed for more than 10 years now, and we can make a movie by collecting all those images and watch the planets go around. So we can actually see a exoplanetary system in motion. So really spectacular. Unfortunately, this remains unique. This is the best case we have so far of a success of the direct imaging method. But it is spectacular. By the way, for scale, these would be the equivalent orbits of planets in the solar system. So these are widely separated planets. They're all at greater orbital distances than Saturn is from the sun. That's part of what made it possible to detect them, is they're relatively far from this bright central star. Okay, so a lot of science fiction is set on planets around red giant stars, like Krypton, the planet that Superman was born on, and somehow the red light from the star is important to his superpowers here on the Earth. So do we know of planets around red giant stars? We do know of a few, but they're not very secure detections. Red giants suffer from the same problem that I was referring to with massive stars. They're very big, so the transit method is out. And as it turns out, their surfaces are kind of unstable. They pulsate and oscillate kind of randomly, and that interferes with our ability to measure planets with the Doppler method. So I wish we knew more about the planets that exist around red giant stars and whether they survive the transition to the red giant phase. For those of you who don't know or who might need a reminder, what is a red giant? Well, here's an animation of the early sun, and now the planets have formed around the sun. The sun spends a few billion years in its current condition before running out of hydrogen at its core and swelling up to become a red giant. That is the sun's future. And then even further in the future, the luminosity of the red giant is so high that it pushes off its outer layers into the surrounding space and reveals a very hot, dense core that was buried within the red giant. And we call that exposed object a white dwarf. So we don't know much about planets around red giants. We do, however, have a pretty good case for a planet around a white dwarf, which I find even more interesting. So this was another test discovery that was followed up with telescopes on the ground that showed a transit of some object across this white dwarf that have exactly the characteristics one would expect from a planet roughly the size of Jupiter. What's fun about this is that here the dip goes down to below 50%, so it blocks 56.65% of the star's light. That's because white dwarfs are extremely dense. Typical one is the size of the Earth, even though it packs the mass of something like half the mass of the sun. So they're very compact objects. They are smaller than Jupiter. And so our artist's conception for this system is an Earth-sized white dwarf that is being orbited by a planet that is larger than the star itself by about a factor of 9 in this case. So that's amusing. It's also interesting that this planet has an orbital period of only a few days. It's very close to the white dwarf. Now, how did that happen? The white dwarf used to be a red giant, which would have enveloped the current position of this planet. So somehow, after the red giant exposed the white dwarf inside, a planet spiraled inward and took up this tiny orbit around the white dwarf. We really don't know the story that led to this configuration. Interstellar was one of the more interesting science fiction movies in the last 10 years. Maybe some of you saw it. It covers a lot of ground in science fiction, but one of the plot elements is about a planet that the astronauts have to visit that is in a star system that includes a giant black hole. And the producers, the writers of the movie have fun playing with the idea of time dilation, the fact that time runs at a different rate for observers near a black hole compared to observers far away. So black hole those are irresistible locations for science fiction. So what do we know about planets near black holes? I'm sorry to say we don't know of any planets that are in systems with black holes. If I had been giving this lecture about maybe more than 6 months ago, I would have said we're actually very far from being able to perform the relevant measurements, because most of the black holes we know about call attention to themselves because they are accreting material from a nearby star, which produces lots of high energy radiation. And that's how we are alerted to the presence of the black hole in that system. What we really want are black holes that are around normal stars that are just living their lives peacefully and happen to have a black hole nearby. But a few months ago, the first such object was detected using data from another relatively new space mission called Gaia. And it was followed up. So by the way, this is what the black hole looks like in the movie Interstellar. It is accreting material from some object causing the surrounding space to glow. But this new object I was talking about, the data that clinched the case is shown here. This is again the Doppler velocity of the star as a function of time in years. And the star is moving around back and forth in such a way as to prove that it is in an elliptical orbit around the center of mass of a system, and the other object is at least 10 times the mass of the sun. And yet we see no light from it. We only see the light of a normal sun-like star. So the authors made a pretty convincing case that the other object is, in fact, a black hole. This is a perfectly ordinary sun-like star, happens to be within shouting distance of a black hole, but the black hole is not interfering with the star. It's far enough away that there could be close-in planets around this star that are not in danger of immediate danger of falling into the black hole. So those same astronomers are gathering even more data, Doppler data, looking for any tiny wiggles in this signal that would betray the existence of planets around that sun-like star. So we may well know in the near future about planets with a black hole elsewhere in the system. Now, how am I doing on time? Should we, when do we want to wrap up tonight? Like 10 more minutes? Okay. So there is another method for detecting planets that might be orbiting black holes that is really interesting and is based on interesting physics. It is not based on Newton's laws of motion or simple geometry like the Doppler method or the transit method. It is instead based on the theory of general relativity, and in particular a phenomenon called gravitational lensing or a gravitational mirage. So I want to explain, even though that technique hasn't worked yet to find planets around black holes, it's interesting and I want to show you how it works. So you've all seen a normal mirage, for example, a road mirage, where it looks like there is some reflective surface up ahead on the highway, even though as you keep getting closer to it, it keeps receding into the distance. What's happening there is that the pavement is very hot, and that causes the air just above the pavement to be hotter than it is higher up. And the gradient in temperature of the air causes a gradient in the optical characteristics of the air, the index of refraction, that causes light that would ordinarily come from the sky and hit the pavement to curve around and go into your eyes as the driver of a car. And so when you look in this direction, it looks like you're looking at the nice bright sky, and that's what gives it this mirror-like or water-like impression. So that's a road mirage. Something similar happens with gravity. The gravitational field and the change in that gravitational field near a star can deflect the light from a more distant star. So the light from the star that would ordinarily go off in this direction is instead bent around and enters our telescope. And the same thing can happen in a different direction. And so if we look with our telescope, it looks like there's a star over here, and then there's another star over here. It creates a fictitious double star. And importantly, the total amount of light we get from those two fictitious stars, those two mirages, exceeds the ordinary brightness of the star. So if the star were to drift in front of a star in the background, even if we couldn't split that double, even if it just looked like a single source of light, we see it rise and fall in brightness as the star passes in front. So this is a phenomenon called gravitational lensing. You can simulate it for yourself if you chop off the bottom of a wine glass, or if you just hold it at the right angle. The curvature of the glass and the varying thickness of the glass has roughly the same effect as the varying gravitational field. So you can create double images and distorted images using this bottom of a wine glass. So for example, if you want to play around with it at home, you can look at a candle flame, or you can make a black dot on a piece of paper and pass this gravitational lens in front of it, and you can see what I'm talking about. It makes multiple images of the source in the background. So the way this works is here's the star, and it's spraying out light in all directions. But then there is a star in the foreground that's moving across, bending the light beams, And we register that here on Earth as a rise in the apparent brightness of this background star. And do you see this little bump here in this brightness record? That's because of the gravity of the planet that this foreground star was carrying with it. That planet creates an extra little blip of brightness. So here is the brightness rise. This is not real data, by the way, due to the magnification of the star in the foreground. And this extra little blip of brightness is because the star in the foreground has a planet going around it. And the gravity of that planet, it's kind of like a little pebble of glass within the wine glass bottom that's denser. And so it produces a little burst of extra magnification that we can see with our detectors. So this is the gravitational lensing method. It's the most exotic method that we have for finding planets. We do not need any light from the foreground star. It all relies on the mass of the foreground star. We don't need to see any light from the planet either. We just use the background star as a source of light, and we're sensitive to the mass in the foreground. That means it's just as good at finding planets around black holes as it would be around ordinary stars. So with this method, there are probably about coming up on 50 or 60, I would guess, planets that have been discovered with this method. They tend to be giant planets or Neptune-mass planets, and they tend to orbit ordinary stars, of course. But there is a chance that future surveys will find planets orbiting more exotic types of stars. In particular, there is a space telescope currently under construction called the Roman Space Telescope that will have a mirror roughly the size of the Hubble Space Telescope, but a much wider field of view for its camera. It's going to do all kinds of great survey work of galaxies and distant extragalactic objects, but it will also spend part of its time searching for planets using this method of gravitational lensing. So it should rapidly advance this subfield. Okay, finally, what about the Earth? Like the most common type of planet in science fiction is an Earth-like planet where people can breathe and we can visit there, and it looks maybe unfamiliar terrain, but basically like the Earth. How close are we to being able to detect planets that truly resemble the Earth? So at the moment, it's hard to point to a single known planet and say, yeah, that really looks like a clone of the Earth. We know of Earth-sized planets and Earth-mass planets, but not that have Earth-like orbits around sun-like stars. Those are just a little too hard for us to detect at the moment. It's easier to detect them when they're closer to the star, because that makes the transits more frequent. It also causes the star to move around faster. By the time you put an Earth-mass planet all the way at 1 AU, that is the same distance from its star that we are from the sun, it's undetectable with our current technology. So we're getting there. We are kind of crawling our way there. I expect that we will be there, say, within 10 years. We might have a nice sample of Earth-like planets using the Doppler method, perhaps the transit method. But that will only increase our hunger to see it in an image. This is the famous image taken by one of the Voyager spacecraft, which Carl Sagan and some others arranged for the spacecraft to look back at the Earth and snap a picture. And this is the Earth, this pale blue dot. So it would be really wonderful to see a pale blue dot like this around some other star, one of our nearest neighbors in the galaxy. That day will probably come over the summer, or maybe late in the spring. A panel of the National Academy of Sciences, which is convened every 10 years to recommend highest priorities for astrophysics for the National Science Foundation and for NASA. That panel said that this should be our top priority for the next decade, maybe even the next 2 decades, to build a space telescope that is capable of this kind of image, to see an Earth as a pale blue dot around a nearby star. We have our new fancy space telescope that was just launched a year ago, the James Webb Space Telescope, which you've undoubtedly heard about. It's doing revolutionary work in cosmology. It's studying exoplanet atmospheres, a topic I haven't even had time to discuss today. However, it is not even close to being capable of imaging an Earth-like planet around a sun-like star. The Roman telescope, the next space telescope, will not be capable of that either. It's several orders of magnitude away from being able to do that. That will take the next space telescope, for which there is only really a rough idea of how it might be built. But the basic idea is that it will probably be web-like, a segmented, gigantic mirror in a large star shade parked somewhere far away from the Earth where there's no stray light. And it will probably have to be about twice the size of the Webb telescope, or maybe even larger, in addition to having a coronagraph or some other type of instrument to block the light from the central star and allow us to search for those pale blue dots. So this is a long way off. It gives us all the motivation to take good care of ourselves so that we're still around 30 years from now when we might be able to enjoy some of these images. So my main message is that science really has caught up with science fiction. And the boundary between science and science fiction is moving. As we get more capable technology, every time we find a better way to measure the brightness of a star or its spectrum, we find more planets. So the scope for discovery still seems large, and we don't seem to be in any danger of running out of things to do. So thanks, folks, for your attention. I'm happy to answer whatever questions you might have. Questions, please.
Going back to the periodic set of
Yeah.
stars and sun, the planets moving amongst them.
Yep.
Are those paths theoretically closed so that the planet is looping and figuring out a way to get back to a starting point and repeating that?
So the one that I showed has a single star with two planets in very closely adjacent orbits. Yeah, that system appears to be stable. You know, when you run it on the computer to simulate the orbital motion, it doesn't fall apart within, say, I don't know, at least 10 million years or however long it's been gone. Yeah, that's not well, it is a three-body problem, but two of the bodies are very small. Yeah. So then there are the circumbinary planets, where there's one planet or several planets all going around a pair of stars. And those two are stable. There's no kind of looping motion in between the stars. That would be very unstable. But these planets are far enough away for them to be stable in the long term. I mean, it kind of makes sense, right? Even if there did exist planets with these crazy figure-8 orbits, they would go unstable rather quickly, and it would be unlikely we would ever spot one in that condition. Yes?
Josh, what are your thoughts regarding SETI and specifically optical SETI?
So SETI is the search for extraterrestrial intelligence. It is usually conducted at radio wavelengths. You use a radio telescope, very sensitive, wide bandwidth. You look at lots of stars and you hope to find some kind of signal that couldn't be of natural origin. So that idea goes back to 1959 in a paper by Cocconi and Morrison. And I think the arguments of that paper are still valid, that the radio spectrum is probably the best place to look. The galaxy is highly transparent at those wavelengths. And it's pretty dark in the sense that there are not lots of bright radio sources that crowd our view. And there's a special radio wavelength. You know, you need to predict where are they going to be broadcasting on the radio dial. And all intelligent creatures will know that there's a special frequency, 1420 megahertz, because neutral hydrogen emits radio waves at that specific frequency. So for those reasons, it makes sense to look in that neighborhood, because any intelligent civilization can anticipate that the others will also be listening to that neighborhood of the spectrum. Optical SETI is, and by the way, I think that's a very reasonable thing to do. I don't think it's crazy. I don't work on it myself because it seems so speculative, and you could spend your whole career working on it, and the null results are not very interesting. You know, if you don't detect anything, it doesn't mean it's not out there. You just could be searching in the wrong place. But I'm very glad that there are some special people who have devoted their careers to that endeavor. Optical SETI is the idea that another recognizably artificial signal would be very narrow laser pulses. There's no natural source of radiation that would have the characteristics of sharply defined laser pulses. So maybe we should search for those. And the great thing about that is the laser pulses would stand out clearly against the light from the star because they are so intense during that pulse. So the glare of the star is unimportant when you're looking for these laser sources. I just don't know why. I haven't thought about the advantages and disadvantages of broadcasting at laser light rather than radio.
It was a verifiable.
Yeah.
Wow.
Yes, and I guess, and I should also add that in no case has there been a confirmed, verifiable signal of any kind. Lots of false alarms that have proven to be of terrestrial origin, of instrumental glitches, and so forth.
Do you believe in the Fermi question?
So I guess you're asking, is there intelligent life elsewhere?
Where is everything?
Yeah, and so Enrico Fermi asked, well, he was skeptical of this idea and said, if there is intelligent life on lots of planets in the galaxy, then surely it would be obvious because there's been enough time over billions of years for their spaceships to crisscross the galaxy. So why aren't they all over the place?
I think the very fact that they haven't tried to get a hold of us is proof enough. I don't think we quite come up to the bar.
To me, it seems like there are enough stars, and now we know there are certainly enough planets. Planets are very common around stars like the sun and other types of stars, that it seems very likely to me that the exact same conditions or similar conditions exist somewhere in the galaxy that existed in the early Earth, or if not here, certainly in other galaxies. There's just so many attempts, so many possibilities that it seems very likely that we are not unique. However, how far away is the nearest one? That's much more questionable. If you're asking about, is there life within 10 light years of the sun? Now we're not talking about billions and billions. We're just talking about maybe a few thousand stars. And it becomes much less obvious to me that there would be. And as for the Fermi question, well, I don't know. It's fun to speculate about the actions and motivations of alien civilizations, but we just don't know. Sure.
I don't know, you may have mentioned it, I didn't catch it. What's the estimate of the total number of verified sightings to date?
Sightings of planets.
Can
So
you-
the
Can you
closest,
just repeat that question?
yes. So the question is, how many exoplanets do we know of with confidence? And the closest thing we have to an official count comes from a NASA database called the NASA Exoplanet Database. Naturally enough, you can Google it and play around with it yourself. And I think it contains about 6,000 entries at this point. And not all of them will turn out to be genuine planets, but most of them will. Maybe like 90% of them are probably true planets. The others masquerade. There are other types of systems that can masquerade as planets sometimes. And then, as I mentioned, the TESS mission has another 5,000 or 6,000 that are pending confirmation. And I expect about half of those will turn out to be planets. So pretty soon we'll be approaching 10,000 planets within, say, 5 years. And statistically, we now know that they're very common. If you pick a random star like the sun, there's about a 50-50 chance that it has detectable planets. And since currently detectable planets are only a subset of all possible planets, it seems very likely that almost all stars have planets.
I have 4 questions here.
Okay, want
Wait,
to take
but
one of
go
those?
ahead.
Mhm.
Oh,
How far away, like, linear they able to find places at this point?
Well,
the question was how far
Yeah.
away you can,
how far away is the farthest known exoplanet? I don't know exactly, but it's probably it's probably like several thousand light years. No, that's not true. Probably quite a bit more than that. Probably like 10,000 light years. And that's because of the gravitational lensing method. That method actually works the best when both stars are pretty far away. So like, halfway across the galaxy or something like that. So yeah, we do know of stars that are really in quite different locations in the galaxy that have exoplanets. But most of them, besides the gravitational lensing method, most of them are within 1,000 light years, and even more of them are probably within a few hundred, which is our little neighborhood of the galaxy. Just for reference, the center of the galaxy is about 25,000 light years away.
We'll take one, we'll take three, we'll take these three here. Does the fact that the star S2 that orbits around Sagittarius A give any indication that there might be planets too that might orbit black holes, albeit at very large distances from the black hole?
Good question. So right at the center of our galaxy is a mammoth black hole. There's very good evidence for a black hole with a mass of not 10 times the mass of the sun, but 4 million times the mass of the sun. It's called Sagittarius A star. And there are lots of stars that are orbiting in the vicinity, not close enough to be in any danger of falling in, but close enough to be whipping around pretty quickly. I think one of the closest ones makes a complete orbit every 15 years or so. So it's pretty close. Unfortunately, it's possible that those stars have planets. I don't remember exactly what kind of stars they are, but we have learned that most stars that we can detect planets around, that we can search for planets, do in fact have planets. It's just that those stars are so far away that we have no way of detecting them from where we are now. So it would be just speculative. That would be pretty interesting, though, if you had a supermassive black hole in your night sky.
Vanderby, referring back to 51 Pegasi B, the radial velocity was plus 70 meters per second on the upside, but was about minus 50 meters per second on the downside.
Ah.
So is it not plus minus 70? It looks like it's plus minus 60. Is it right? I guess he's getting a little nitpicky. I don't know.
I can count on Bob to be very observant. Yeah. So I actually did not notice that. I mean, that does happen because the center of mass of the planetary system is not likely to be at rest with respect to our frame of reference. The star has some random velocity in the galaxy. So that will cause an overall redshift or blue shift, which lifts that the baseline up or down. And then the planetary signal is on top of that. So maybe that's what's going on in that figure.
That's exactly what I was wondering.
Then one other last one, they repeated it twice, which is good. Got my attention. Why is the 1420 megahertz frequency actually a good thing to do SETI search at? Wouldn't there be tons of interference from all the neutral hydrogen?
Yes. So first of all, the signal from neutral hydrogen is not kind of overwhelming, that if you were broadcasting with a powerful antenna at that frequency, it's very easy to outshine the diffuse clouds of hydrogen gas. So it wouldn't actually, I think, be that hard to stand out. But because it's just a special region of the spectrum, people have argued that we should search, tune the radio dial to 2 times 1420, or pi times 1420, or 1420 over 2. Frequencies that are related to that hydrogen frequency might be the natural choice for a broadcasting civilization. Mm-hmm.
If I can add to that, when we were doing study over Observatory with Wilkinson, we were also, and Bill was part of that too, we were looking for a signal that would be unique, that would not, as far as we know, be able to be created naturally. And thus we were looking for, if I remember this right, Bill Murray, for signals that were in the millions of a second, something that nature was not creating at that particular, I remember it was like billions.
Yeah, nanosecond pulses is what I've heard. It would be really interesting to detect anything like that, natural or artificial.
We're still here, so we did.
Yeah.
Otherwise, we would be Johnny Carson.
Yes.
So, besides currently operational missions, what's the next big thing that NASA
So yeah, what's the next big NASA contribution to this field? So first of all, the Webb telescope is new. It really only started gathering scientific data last summer, and it's already making a huge impact on the field. And that's because it's able to study exoplanet atmospheres using the transit technique. So when the planet goes in front of the star, some of the starlight filters through the planet's outer atmosphere before it makes the journey to us. And so it makes an imprint on the spectrum that we observe from that star. And we've been able to perform those measurements before, but they haven't been very good. And so Webb, though, is extremely capable of making such measurements. So it can detect molecules in the atmospheres of planets this way, and has done so already for several giant planets. So that's the first, like, that's the here and now of this field, I would say. After that is probably the Roman telescope that I mentioned, that will do a very comprehensive survey using the gravitational microlensing technique. So that, I think, is scheduled for launch in 2027, which means maybe 2028, 2029. Yeah.
Right now, the planets we're finding, the kinds of planets we're finding, are biased based on our detection method.
Yes.
How's that going to change?
Yes. So that's a very good point. All of the sample of known exoplanets is not a representative sample of all the planets that are in our neighborhood of the galaxy. It is strongly biased towards big planets, massive planets, planets on close-in orbits, because all of those things make it easier to see the planet through the transit and the Doppler methods. So what happens is we build a new spectrograph that is capable of better Doppler precision. That allows us to go to either smaller planet masses or wider orbits, both of which cause the signal to be smaller. So it's been kind of a steady progress in that direction. So right now, maybe 10 years ago, our best spectrographs could measure signals of a size 3 meters per second. And the best ones today are more like 0.3 meters per second, maybe 0.5. And to get to an Earth, we have to go to 0.1 meters per second, or even a little bit better. So our detection limits keep creeping out as our technology gets better. The same is true for the transit method. The reason we need space telescopes is because it's very difficult, maybe even impossible by today's technology, to be sensitive to changes of parts per million in the brightness of a star when you're underneath the Earth's turbulent atmosphere. So we build a better space telescope, we'll find smaller planets. Anything else? Okay.
Please remember also that besides the detection threshold, the sample of the total sky is quite minimal. That's another reason why the database is kind of biased.
That's right. Yeah, certain missions or projects have only looked at small parts of the
Small
sky.
percentage of the sky.
TESS is an exception, though. The whole reason for designing the TESS mission was that we want to survey the entire sky. So by this point, I would guess maybe 90% of the sky has been surveyed by TESS. It doesn't find all the planets, though. It only finds the transiting ones, and it only finds the really close orbiting ones.
Yeah.
But it is surveying almost the entire sky. Yeah.
When you read the articles about these discoveries, it'll often say, 4,000 exoplanet candidates.
Right.
Have been. What does that mean?
Yes, that mostly comes from the transit surveys. When you see a star go blip, blip, you can't be sure it's a planet, because it could be a binary star, which would ordinarily produce huge dips, but there's a third star in the system that's brighter than either of the two. And so the variations in the total light are small because of the constant light from that third star. So those are kind of annoying, and they take time and other types of observations to rule out. So there are other kinds of false positives, that is, stellar systems for which the signals look like planetary systems. That's why there's so many candidates. Yeah.
How far away are we from getting more data than we can actually look at? We depend on AI and all these other things to do this analysis.
Yeah.
and more and more.
We're right at the transition where we're collecting so much data that these new techniques are almost necessary. I don't think that astronomy is yet big data on the same scale as Google and OpenAI and all of these breakthroughs that we're hearing about in machine learning. We don't produce vast amounts of data by the standards of many commercial enterprises. But we are producing more data than we faculty members and graduate students are used to dealing with. And so it's kind of fun to see that many of our new graduate students are very excited about these methods of machine learning and all kinds of other new algorithms for sifting through large databases and know quite a bit more about it than we do. In my own group, I'm seeing that as well. So there's a lot of interest from young people in that area, and we do have these giant data sets for them to get busy with.
Do citizen science projects, do you think have any role in
yeah.
exoplanets?
Do citizen science projects have a role? I'm glad you mentioned that because I forgot to describe. There is a citizen science project associated with TESS. It's called Planet Hunters TESS. It's kind of the opposite of the machine learning big data approach. The idea is that you get lots of people with their own internal neural networks to look at these light curves, to look at graphs of brightness versus time, and see if they spot things that our algorithms have for some reason missed because of some complication or another, or because they're not exactly what we programmed the algorithms to look for. So if you register with Planet Hunters TESS, you can look through light curves, you can discuss any weird things you find with the scientist who runs the website. And they have tens of thousands of people classifying light curves. So that is, I think it's the only citizen science project I'm aware of where there's a genuine chance of exoplanet discovery.
It's a parallel processing technique when you think about it.
That's right, yeah. It's a parallel processing neural network. Well, one last comment I wanted to make because I've recorded a couple of courses for the teaching company, which also calls themselves Wondrium these days. One is about exoplanets, and one is a more general introduction to astrophysics as a whole. And I'll have a book coming out in July by Princeton University Press called The Little Book of Exoplanets. So if you are interested in learning more, these are some possible resources. All right, thanks again, everybody.